Welcome to the deep dive. Today we're tackling something really foundational, the bedrock of computing, basic data types.
Yeah, it sounds simple maybe, but it's crucial.
Absolutely. And even if you've, encountered this before, maybe in programming or just reading about tech, we think sticking with us today will be valuable.
Definitely. Understanding these core pieces gives you a surprisingly powerful way to see how computers actually store and handle information.
Think of it like getting the foundational grammar right. It provides this lasting clarity for everything else in the digital world. We want this knowledge to really stick with you.
That's a great way to put it. I mean, think about all the stuff we see, daily text, pictures, videos, numbers.
Everything.
Right, everything. And underneath all that complexity, it's built from these basic types we're going to unpack.
It's like knowing atoms to understand molecules, perhaps?
Sort of, yeah.
Yeah.
A good analogy. It helps make sense of the bigger picture.
Okay, so that's our mission for this deep dive. Really get into these fundamental units. We want you to walk away with a clear, solid understanding of what they are, and maybe more importantly, why they matter, why their differences are important.
Yep. So we'll be covering integer types.
Okay.
That's things like byte, short, int, long.
But then the ones for decimals, floating point type.
Perfect. Float and double.
We'll look at the character type char.
For text and symbols.
And wrap up with the Boolean type, bool, true or false.
That's the plan.
All right, let's jump right in. First things first. What are basic data types fundamentally in computing?
Okay, so at their core, basic data types are the most fundamental kinds of data that the computer's brain, the CPU, the central processing unit, can actually work with directly.
Directly.
They're like the raw ingredients, the absolute basics for representing any information inside a computer. Think of them as the nouns and numbers that algorithms, those step-by-step computer instructions, operate on.
Okay, raw ingredients, but how does the computer know what's what? Like, my computer doesn't inherently understand A or 10, does it? It needs some way to represent them.
You're exactly right, it doesn't. At the very, very bottom level, every single one of these basic data types gets stored using binary. Just sequences of zeros and ones.
The famous zeros and ones, on and off switches.
Precisely. Each one of those zeros or ones, that's a single bit, a binary digit.
Okay.
And for practical reasons, computers usually group these bits together.
And that leads us to bytes, right?
Exactly.
Yeah.
In pretty much all modern systems, a byte is made up of 8 bits.
Take this, okay.
And grouping them like that into an 8-bit byte lets you represent 2 to the power of 8.
Which is 256.
Right. 256 different combinations or values. And this ability to hold a specific range of values, that's really key to understanding the different data types.
Gotcha. So bits build bytes, and bytes give us a range of values. Now let's connect that to those integer types you mentioned. Byte, short, int, long. They're all for whole numbers, but how do they differ?
The main difference is just how much memory, how many bytes each one gets. And that directly affects the range of whole numbers they can hold. Let's use Java as a starting point. It's quite clear there.
Okay.
So in Java, a byte uses, 1 byte, 8 bits,
Makes sense.
which gives it that range of 256 values. But since we need negative numbers too, it goes from -128 up to +127.
Okay. So -2 to the 7 up to 2 to the 7 minus 1.
Exactly. And its default value is just 0. Think of it as a small box for small whole numbers.
Right. Small box. What about int? That one seems to pop up everywhere. It feels like the standard integer.
It really is the workhorse, you're right. In Java, an int gets 4 bytes.
So 32 bits.
32 bits. That gives you a much, much bigger range, from -2 to the 31 up to 2 to the 31 minus 1.
I mean, a lot bigger. Over 2 billion each way, roughly.
Yeah, it's a substantial range.
Mm.
Default is also 0. You'd use this for most general-purpose whole number stuff, unless you know you need something tiny or absolutely massive.
Okay, so more bytes means a wider range. And you also listed short and long. Where do they fit?
Right, so short in Java is 2 bytes, 16 bits. It sits between byte and int. You might use it if you're really trying to save memory and you know your numbers won't get too big.
Kind of niche, maybe.
Sometimes, yeah. Then long is the big one. 8 bytes in Java, 64 bits.
Wow.
Yeah, the range is enormous. You use that when you're dealing with potentially huge numbers, like maybe counting milliseconds over decades or something like that. Numbers that would definitely overflow an int.
Okay, so Java seems pretty consistent there. Byte, short, int, long, 1, 2, 4, 8 bytes. But you mentioned this might not be the same everywhere. Programming languages can be quirky.
That's a really crucial point. These sizes aren't universal. Take Python, for example. Its int type is super flexible.
How so?
It basically grows as Nuit. It's not fixed at 32 or 64 bits. It can become arbitrarily large, limited only by how much memory your computer actually has.
Whoa, okay, so no overflow errors just because your number got too big for a standard int.
Exactly. It makes life simpler in that respect. You don't have to worry about picking int versus long quite so much.
Sounds handy. Any downsides?
Well, potentially. There can be a small performance or memory overhead compared to fixed size types because the system has to manage this dynamic sizing. Now, contrast that with languages like C or C++ Air.
Ah, the classics.
Right. There, the size of an int. It's not strictly defined by the language standard itself.
Really? So it can change?
It can vary based on the compiler, the operating system, the computer architecture.
Yeah.
Is it 32-bit, 64-bit?
So my int in C on my Windows laptop might be different from an int on a big Linux server.
It's possible, yes. For instance, there's something called the LP64 data model, common on 64-bit Unix systems like Linux and macOS. They're long as 64-bit, but int often stays 32-bit.
Okay.
So developers in C or C++ have to be mindful of this for portability. But look, the key takeaway isn't memorizing every specific size in every language.
Right.
It's understanding the concept. Different integer types exist for different size needs, and they use different amounts of memory to achieve that.
Got it. Concept over specifics. So integers handle whole numbers. What about decimals? Numbers with fractional parts. That's floating point territory, right? Float and double.
Exactly. Floating point types, float and double, are for representing numbers that have, decimal point. Real numbers, basically.
How do they work? Is it just storing the digits before and after the point?
It's a bit more complex internally. They use a system kind of like scientific notation storing a sign, the main digits, a significant or mantissa, and an exponent. This lets them represent a very wide range of values, both very large and very small, but with a certain level of precision.
Okay, and the difference between float and double, is it size again?
Yep, primarily size and therefore precision and range. Back to Java. A float uses 4 bytes, 32 bits. A double uses 8 bytes, 64 bits.
So double is, well, double the size.
Right. And that means double gives you significantly more precision, more accurate decimal digits, and a much wider range of possible values than float.
So if I'm doing, say, scientific calculations, I'd probably want a double.
Generally, yes. Or financial calculations where precision is critical. Float might be okay for things like graphics, where absolute precision isn't always the top priority, and you might want to save memory. The default for both in Java is 0.0. Often you'll see a little f after a number like 3.14f to explicitly say it's a float.
And Python, does it have both?
Python just has float, but its float is actually a 64-bit double precision number, like Java's double.
Ah, okay. So Python simplifies again, just giving you the high precision one by default.
Pretty much, yeah. It aims for ease of use there.
All right, so integers for whole numbers, floats, and doubles for decimals. What about text? Single letters, symbols, that's char, right?
Correct. The char data type handles individual characters. Letters, punctuation, digits treated as text, symbols, even emojis.
Emojis too, okay. How much space does one character take? It feels like it should be small.
Well, let's look at Java again. In Java, a char takes up 2 bytes, 16 bits.
2 bytes? That seems like a lot for just one letter A. Why so much?
Good question. It's because Java uses the Unicode standard. Unicode aims to represent characters from basically all writing systems in the world. English, Greek, Cyrillic, Chinese, Japanese, Korean, Arabic, emojis, mathematical symbols, everything.
Ah, okay. So 8 bits, the 256 values from a single byte, just isn't enough for all that?
Not even close. To give every character a unique code point, you need more space. 16 bits gives you 2 to the 16, which is over 65,000 possibilities. That covers a huge chunk of common characters. The default char in Java is the null character, basically value 0.
So it's about global compatibility. It makes sense. Does the size always depend on Unicode, though? Or can it vary?
It can vary depending on the specific encoding method used. Unicode defines the character and its number, but encoding is how you actually store those numbers in bytes. For instance, UTF-8 is super common on the web. It's a variable width encoding, meaning it uses 1 byte for common English letters and symbols, but maybe 2, 3, or even 4 bytes for less common or more complex characters. It's efficient for largely English text, but can still represent everything. Character encoding is a whole fascinating topic itself, maybe for another time.
Huh. Noted. A future deep dive.
Right.
So how do other languages handle char? You mentioned Python earlier.
Right. Python actually doesn't have a separate char type. A single character is just a string of length 1.
Okay, simple again.
Yeah. Whereas in C and C++ today, char is typically just 1 byte, 8 bits. Historically, that was often tied to the ASCII encoding standard, which fits nicely into 1 byte, but only covers English characters, numbers, and basic symbols. Modern CC++ often uses UTF-8 or other encoding, so a logical character might still span multiple char values sometimes.
Interesting how these seemingly basic choices differ across languages.
hmm
Okay, we've done whole numbers, decimals, text characters, what's left, boolean, that bool, true or false?
Exactly. The Boolean type, often called bool, represents logical truth values. It only has two possible states, true or false, yes or no, on or off.
Absolutely fundamental for making decisions in code, right? Like
Yeah.
if statements.
Totally. All conditional logic, loops, controlling the program's flow, relies heavily on Boolean values.
How much memory does a true or false take? It feels like it should only need 1 bit.
Logically, yes, you only need 1 bit to represent two states. But in practice, like in Java, a bool usually occupies 1 full byte.
1 byte again. Why not just 1 bit?
It comes down to how computer hardware, the CPU, and memory are typically designed. The smallest chunk of memory that most CPUs can easily address and work with is usually a byte, 8 bits.
So it's inefficient for the CPU to handle individual bits directly.
Generally, yes. It's easier to just use a full byte, even though you're only technically using 1 bit of the information capacity within that byte. The other 7 bits are just unused, essentially, for that Boolean value. The default value for a bool in Java is false.
Fascinating. A little bit of waste for the sake of efficiency at a lower level. Okay, so we've covered the main basic types: int, float, char, bool, and their variations. Now, how do these relate to data structures? People talk about arrays, lists, maps. Are those related?
That's a really important distinction to make clear. They're related but distinct concepts. Basic data types are about the kind of data. Is it a whole number, a decimal, a character, a truth value? It defines the content type.
Okay, the content.
Data structures, on the other hand, are about organization. They are ways of arranging and storing collections of data, maybe collections of these basic types, to make them easy and efficient to work with.
So structure is the arrangement, basic type is the stuff being arranged.
Exactly. Think of it like
Yeah.
building blocks. The basic data types are like the individual Lego bricks, red 2x2 brick, blue 1x4 brick. The data structure is the thing you build with those bricks, a wall, a car, a house. It's the way you organize the bricks.
I like that. So an array could be the wall structure.
Right. And you could build that wall using only integer bricks or only floating point bricks or maybe even a mix in some cases. The structure, the wall, the array, is separate from the type of brick, integer, float being used.
Can we see that in code? Maybe just conceptually.
Absolutely. Think about an array or a list, a common data structure for holding items in sequence. In Python, you could have numbers 1, 2, 3. The list is the structure. The fact that 1, 2, and 3 are integers, int, is the basic data type, or temps equals 98.6, 100.1, 99.5. Same list structure, but now holding floating point float types.
Makes sense.
In C, you might write int ages 3. This signifies the array structure, and int specifies the basic data type it holds. You could just as easily have float prices 3 or char initials 3.
Or even bool flags 3 for true-false values.
Precisely. The structure of the array provides the container and the organization, while the basic data type defines what kind of thing goes into that container, the what versus the how.
That really clarifies it. The structure is the organization method. The type is the nature of the items being organized.
You got it.
Yeah.
And some languages, like Python, even let you mix types in one structure, like stuff equals 10, hello, true, 3.14. That really highlights the separation between the container, the list, and the types of things it can hold.
Wow. Okay. This has been super helpful, really breaking down these fundamentals. So let's bring it back to you, our listener. Why spend time getting this deep understanding of, seemingly simple types? How does knowing about bytes and floats and bools actually help you, whether you're technical or just curious?
Well, I think this knowledge provides a really solid foundation. When you hear about more complex topics like how databases store information or why certain algorithms are faster than others or how file formats work or even just understanding error messages you might see, having this grasp of the basic data types underneath it all gives you crucial context. It helps demystify a lot of the jargon.
It stops it from feeling like magic.
Exactly. It removes some of the magic. You start to see the building blocks. You understand that fundamentally it's all about representing different kinds of information using these types, stored in binary and organized by structures. It makes you less likely to feel overwhelmed by technical details because you can relate them back to these core ideas.
It's like having a mental model that holds true across different technologies.
Precisely. It's knowledge that lasts because it's so fundamental. It helps you think more clearly about how digital information actually works.
I agree. So, quick recap then. Basic data types. The fundamental kinds of info a CPU works with. Directly integers, floats, chars, bools. Represented in binary, bits and bytes. They define the what of the data. Data structures like arrays or lists define that how that data is organized.
That sums it up nicely. And really getting that distinction, understanding those types, is a huge step towards feeling more comfortable and knowledgeable in our digital world.
Absolutely. So here's a final thought for you to chew on. Think about all the digital information you use every day. Your emails, the websites you browse, photos, music, games, everything.
Hmm.
Knowing what you now know about these basic building blocks, integers, floats, chars, bools, all stored as zeros and ones, how does that change how you perceive that information being stored and processed? Does it make you think about limitations? Like why photos sometimes look blocky, or why calculations might have tiny errors, or possibilities, how these simple types combine to create such incredible complexity.
Yeah. What are the boundaries and what are the frontiers dictated by these fundamentals?
Something to ponder. Reflect on that, and we'll catch you next time for another deep dive.